Hello, everyone. Welcome to Homework for P2 Bootcamp. My name is Gabriel, and I'm one of your TAs, and we'll be walking you through the whole Homework for P2 process. So, to get started, we would recommend you to join the Kaggle competition, and you can access the starter notebook by clicking on this link and also the write up. So the early submission or preliminary submission deadline is on the 10th of April. Unlike other homeworks, you wouldn't get a penalty for not respecting this deadline, but you have 5 bonus points, which you'd get for making the submission before this deadline. And of course, it shouldn't be a random submission, so you should obtain an 11 distance of 50 on Kaggle before this deadline. And you're also requested to complete the homework for quiz, which is available on Canvas, before the preliminary submission. So for this homework, there are some restrictions. So you're required to use attention techniques, although there are no parameter limits, but you should use attention techniques. So using just the LSTMs or RNNs as in homework 3P2 is it's prohibited. So you must use attention techniques. And the final submission is on the 26th of April. So the deadline for the code submission will be announced later, as well as the medium and high cutoffs. So to get started, where we recommend you to start is the write-up. The write-up has almost all the information which you would need to successfully complete the assignment. And if there's some parts of it which you don't understand, we would strongly recommend you post a question on Piazza or attend office hours to gain clarification before starting the homework. So in this assignment, we would be working with the transformer models, which are behind large language models and which have revolutionized a lot of NLP tasks. So in this homework, we'll be building a speech transformer, which is capable of performing speech recognition tasks. So at the end of this homework, we hope that you must have understood and you're able to implement a transformer architecture to solve sequence to sequence problems, to set up an encoder with multi-head attention and self-attention, to set up a decoder with cross-attention, multi-head attention, and self-attention, and how to use attention with masking, and of course, again, and how to use positional encoding. So those are the homework objectives, and of course, part of it is you learning how to tune parameters, hyperparameters, and other training techniques like the incremental training and freezing and unfreezing some parts of your network to enforce some specific kinds of learning. So in the write-up, we define like the problem specifics, which are exactly what you would be doing in the assignment, some notes on you getting started early, and how the starter notebook is structured. And we also have some other section, which is like the notebook walkthrough, which explains every section which you'd see in the starter notebook. So that's why we recommend you going through this write-up before actually starting to code. And we also explain how the data set is structured, and again, the speech transformer which you'll be implementing. So this section has a more details, and we split it into the encoder part and the decoder part. So we strongly recommend you go through this before starting to code. And of course, we explained how we are going to be training and how we are going to be doing the inference, which is different from other methods, which involves just calling the forward method. But here we'll see some slight uh, variation in using like what we call like auto-regressive networks, where the output at a particular time sequence will be fed as the input to predict the next token. And here we also, in the write-up, we also list some common errors which you might face and how to complete and how to resolve them. Another very important section in this write-up is the appendices, where we explain in more theory and mathematical approach on what various components which you'd be using are. So we really recommend you read them up, because they're also going to help you. They're also going to help you in your quiz on Canvas, as well as fine-tuning your models. So it's good to understand the theory behind a lot of components which you'll be using in this assignment. So right now, I would go over to the starter notebook and have a walkthrough on how it is structured. So to access the starter notebook, again on the post, you can click on the post, which should open a new tab, and you can download it or open directly with your Colab if you're using Colab, or you can download and load it to Cargo, which you're using Cargo. And as a note, this model, this assignment can run on a Colab instance or Cargo instance. We, the TAs, have tested to ensure this. So please feel free to use your Cargo or Colab and save your compute, AWS compute for your projects. So we've already spoken about the learning objectives of this homework, and I would just walk through them again briefly. So first, understand the transformer architecture, which is key, which a lot of deep learning applications are currently using, and develop the encoder and decoder modules. So understand how the individual components of the transformer come up together, including like the positional encoding, the multi-head attention, and feed-forward projections. So integrate the complete transformer model. So the transformer model has a lot of moving parts, which you'll see later, but one of the learning objectives is, if we give you these learning parts, can you actually bring them up to form this transformer model? And you should understand the value of multi-head attention and how it's significant to help the model focus on different parts of the input sequence simultaneously. And one very important part of this homework is understanding and applying pre-training techniques. So because we have a lot of moving parts, we have like the encoder, decoder, we have like input embeddings, and so many parts of the transformer architecture, and all of them, they have maybe like a different rate of learning, or they have a different rate of learning, and how their weights are to be updated are different. But so training all of these components at once can be very, very difficult, and it requires a lot of data. So one thing we want you to learn by the end of this homework is how you can apply some pre-training techniques, like using an LSTM as a transformer encoder, a pre-trained LSTM model as a transformer encoder, so that we make just the decoder to learn, and later on adding the transformer and transformer encoder layers on top of this LSTM, and freezing both the LSTM and the decoder to force just the encoder to learn with the amount of data which we have. So this is part of our objectives, which is covered under like the pre-training and training efficiency through strategic freezing. And of course, at the end, you learn how to experiment with different hyperparameters of your model. So to get started, again, here these links are already indicated in the first part, which it's about the Kaggle competition and some of the resources. So we would strongly recommend you read this pitch transformer paper and the attention all is all you need paper to fully understand what you'll be doing in this assignment. So of course, we would start by installing some libraries which we're going to need. We proceed to importing all of them, and I think you're already familiar with this. We just have some few additional imports, Seaborn and Matplotlib, which we'll be using to visualize the attention weights. And unlike previous assignments, we are providing you this time with a standard, with a more enhanced way of saving your configurations using like a YAML file, a YAML file type. So here we've already set up some training configurations for you, and we have the limit of the parameters which you should try. So you can divide this among yourself in your study groups to do your ablation studies. So we strongly recommend, after reading the papers and going through the write-up, you should understand what each of these configs mean, like what's D model, what's DFF, or here it's like the dimension of the feed-forward network, the dimension of the model, and they're pretty much standard, and they're used across so many papers as with the same abbreviation. So please look into that and know what all of these parameters mean, because you'll be using them later. And so we write them into a file and we save them, and then we load them. So yeah, please enter your name so that your study group members can easily know who performed what ablation and what it's working. So if they have like some troubles trying to replicate your results, they can always reach out to you. And the next part is your Kaggle download and dataset download and setup. So you're already versed with this. Please enter your username and your key to install Kaggle, and you download the competition data and unzip it. And next, it's about our vocabulary. So unlike in homework 3 P2 and homework 1 P2, where you were trying to predict the phonemes, here we'll spell the actual letters in the English alphabet. Yeah, so this is a much more difficult task than the phonemes, because we have like some silent characters like N in no, K in no, which would be difficult to predict. But however, we still need our model to be able to emit such tokens. Yeah, but with phonemes, maybe no and no would have the same phoneme, so it wouldn't be a problem for the model for a speech recognition system to predict the phonemes or emit the same phonemes. But for character-based predictions, such kinds of problems begin to occur, and that's why we are like employing things like attention mechanisms to also learn to predict such tokens. And so like the silent no, how will you differentiate it with like maybe just a space it's a very difficult task in speech recognition systems once we are dealing with actual English alphabet. Nonetheless, in this homework, we will be trying to accomplish that. So as pertaining the data set, we've given you all the data set class because we believe by now you're very familiar with the audio data set, and you know how to load like the MFCCs and the transcripts. However, we have some to do here. So in the in the decoder part, we're shifting like our target, and we have some shifted targets and we have targets golden. So please try to understand why we are doing this. If you read the write-up and the papers, you should be able to understand why we are doing that. And after understanding why we are doing this, then you can uncomment them. Nonetheless, the data set class remains the same as like in homework 3P2, where we also have like the collect function to ensure that the sequences in the same batch are of the same dimension. We are doing this by padding with some pad tokens, which we have already defined. And here you can apply some frequency or time masking if you wish. Yeah, but remember, if you're to apply like frequency masking, then you will need to transform your data to the frequency domain and apply the masking before going back to the time domain, because by default, our values are in the time, our MFCCs are in the time domain. So the test dataset class, it's also, you're already familiar with this, and this do not have any change from homework 3P2. So here you're expected to enter the path to your data directory, which might be different depending if you're working on Cargo or if you're working on Colab. And the partition, so we are providing you two data partitions, train clean 50, which is half of train clean 100. However, they are from different distributions, so they are not, train 50 is not a subset of train 100, just to emphasize that. And here, if you are applying substrate normalization, then check the config and see what parameter you need to enter here. And in terms of the data loader, it remains the same as in homework 3P2, but please make sure you configure your batch size accordingly, depending on your compute capacity. So here we perform some sanity check, which is what you've already seen in previous homeworks. So addition here, because in performing, we need to know the maximum sequence length, the max length sequence, and also the maximum transcript length. We perform some data verification, but you're not required to execute this code. But if you have some difficulties, then we recommend you to run this to just ensure that your data set was downloaded correctly and you have the right parameter, the expected parameters for the max MFCC length and also the max transcript length. So the rest of the notebook is divided into two sections. So we have part one, which would take you up to like the preliminary submission, and we have part two, which is like the full transformer. So in part one, what you'll be doing mainly is implementing the decoder part. So if the transformer has the encoder and decoder part, so by reading the write-ups and the papers which we've linked, we hope that you have like a comprehensive understanding of the encoder and decoder part. So in the first part, we are using a simple CNN LSTM as an encoder. So this was trained on homework 3P2, which involve like which was which involves extracting the representations of the MFCC. So here we're also trying to show you that if you already have a working system that is able to extract these representations, then you don't need to learn that sequence again from scratch. We can do some enhancement on that feature extraction part of it, or that encoding part of it. Yeah, but without any enhancement, it should also work as expected on a new problem. So this is given to you. You do not need to implement anything, and we also do not recommend you modifying this class, because we're going to be loading a pre-trained weight, and our weights are according to the configuration of this class. So except you have your own model, your own homework 3P2 encoder and the checkpoint, then you can go ahead and bring in your class here and also load your checkpoint. But for the preliminary submission, we do not recommend you going through this, because the focus is on you implementing the decoder part. After you've implemented the decoder, then for your improvements, you can go through, you can make this change. So we're going to be using this CNN LSTM encoder as our encoder. So, and we'll pay focus to just the transformer decoder part. Okay, so by now you should be very versed with this figure, and we should know what like our targets are. These are, of course, like the characters which we want to predict, and we have to convert them to some embedding, add some positional encoding to understand the position of the target, and we perform some masking, multi self attention to prevent the model to prevent the decoder on focusing on some parts of our input sequence. So of course we need to prevent it to look ahead, because that would be cheating, and we do so with various masking. Like we have to add the path mask, we have to add the causal mask. So please read the write-up to understand what all of these are about. And of course we have these skip connections and layer normalization, which will help us to normalize our output values across the layers. And here we have our multi-head attention, which gets some parts from the encoder, right? So here this edge comes from the encoder. So we have some of the inputs coming from the self attention, and another one coming from the encoder. So this is what we are calling as our cross attention, but it's also just an attention, a multi-head attention module. And again, we have our layer normalization and skip connections. Then we have a pointwise feed-forward neural network, layer normalization, skip connections, and a fully connected layers for our classification. So here, in order to complete the decoder part, the first question, we'll have some questions which we would want you to ask yourself, and which is, can you separate the decoder layers from the whole decoder? So here are the decoder layers, which we can have n of them, but the whole decoder is the whole of this section. So if you can do that, then it will be easy for you to understand this class, which we have like the decoder layer class. And can you also, how many multi-head attention modules do you have to create? How many layer normalizations, and how do we make the residual connections? It's important to note that we've given you a lot of parts for this homework. Okay, so a lot has been given to you under the utilities. So if we check the introduction over here, which has the full transformer and how we are going to be training this transformer, we have a section dedicated for the utilities. So here we've given you different masks, mask 1, mask 2, and mask 3. So some of them are like the attention mask, the pass mask, the padding mask, and the causal mask. So your duty is for you to look at the implementation and know which mask is which, because you need them in the encoder and decoder part. So, but since we are providing you the implementations, we want you to at least understand what they are doing. So that's why we changed the names, but you can call the modules once you understand which mask belongs to or which part. And also we have like the scale dot product, which is an efficient way of computing like the attention in multiple dimensions. So here we'll be dealing with just one dimension, which is like the time dimension. But if we think about this raw speech input, it has like a time and frequency dimension. And in this case, a scale dot product attention mechanism would help you to efficiently compute the attention weights in all of the dimensions. And we have some other utility functions which this will help us to save the attention weights, which is needed for us to understand if our model is converging or not. And of course, we have the multi-head attention modules, which is defined in the architecture. So and after the multi-head attention module, then we have what we call the transformer module. So these ones, where all of them, they are like just utilities. And for transformer modules, we have the positional encoding, the feed-forward neural networks. All of these have been given to you, so you don't need to like recode them, but we recommend you that you look at these functions, look at all what they're doing, if it makes sense to you before start using them. So if we go back to the decoder class, then the decoder has two parts: the decoder layers and the full decoder. So for the decoder layers, look at the architecture which we've given to you and see how these layers connect with each other, because you need that in the forward, and how many of them are, how many of each module you need. So for example, here I need a layer normalization here, I need the layer normalization here, I need the layer normalization here. So that's why you would come and we would see layer norm, three layer norms, and two multi-head attentions, a feed-forward network, and a dropout, which you would use to implement your skip connection. So where the bulk of the work is actually connecting these components together. So for example, once the first thing is in this layer, what do we receive? We receive in the embeddings plus the positional encoding. So we have an input here. Where does it pass? Where does it first get into? So as we can see, it first gets into like the mask multi-head attention. So we will need to do some masking before passing it into the attention, as well as now doing some other skip connections, creating some residual connection, and then do the layer normalization. So if I am to do the forward method, that's why we say first thing is for you to mask your targets, right? And after you do your targets and pass it through the multi-head attention, then we have now our first skip connection. So this section, these first two to do items will actually just correspond to this first section here. And then that's how you continue with the implementations of the decoder layers. And now, after you're done with the decoder layers, we can now move on to the decoder. So for the whole decoder, we see that we have our target embedding, the positioner encoding, the final linear layer for the classification, and also some dropout. So here is it. We have the target, positioner encoding, our decoder layers, and the fully connected linear layers for classification. So those are also here. And now, how do we pass them through it, right? How do we pass them? How do we propagate them, right? So here we've created the decoder layers for you, okay? So we can see it's just a module list of the decoder layers. So according to the number of layers, which is a hyperparameter, we help you to create like the decoder layers. So, but you would have to pass through the decoder layers. So the output of the positioner encoding plus the embedding targets, you need to pass them through your decoding layers. After in here, and the output of your decoding layers, you need to pass them through the linear layer for classification. And we've also implemented this recognized greedy search for you, which will be needed during inference once you're trying to decode the outputs of your decoder. So please, we expect you to already understand what greedy search is from homework 3P2, and this implementation is already done for you. Of course, if you want to explore more, you can try also with a beam search technique, which we haven't given, but maybe you can also try that. And next is the model setup. So we have the CNN LSTM encoder given to you, and now you've completed this speech transformer decoder. So let's combine all of them together. So we initialize our encoder, we initialize our decoder, and then we do some initialization. You can try with some different initialization scheme. And we define the forward method, and we also define a recognize function, which we are going to call during inference. So you're not expected to do anything here. And then we now have the model setup, which uses the speech transformer class to actually build an instance of the model. So here we've given you the max sequence length, okay, and you can check for the data verification part. If it's different, then you should maybe change this value, okay. But this value was based on train clean 100. So if you're working with train clean 100, it shouldn't be a problem to you. And of course, we just want to count the number of parameters. There's no parameter limit, but you would understand after your ablation studies, you would understand that maybe you understand how the number of parameters in your network vary with your performance. So we've provided a checkpoint which will help you with the CNN LSTM encoder. So please load them. It's included in your data directory once you download the data. So depending on whether you're working on Kaggle or Colab, the path might be different. So next, we define our loss functions and also the mix precision training, which has also been implemented for you. So by now you have experimented with different optimizers and different learning rate schedulers, but one of the easier ways, we want to show you one of the easier ways to set up your ablations is defining the configuration like you did above. And here you actually just read from that configuration and initialize the right learning rate scheduler or the right optimizer. So we know from your previous assignments, from the submissions we've gotten so far, you try to like change this value by commenting them out. But if you keep all your configurations on one place, and this is a more organized and cleaner way to do it. So you can also change these parameters as you wish by examining how the training of your model is actually progressing. And so we also have some utility functions given to you to save your models and save some metrics which you can use later on to compare different model checkpoints. So for the training and validation, all these functions have been given to you to convert the indices to characters and calculate the Levenstein distance. So you do not need to make any modifications here also. And we have the train model function, which is also given to you, which takes the model, the train loader, and the optimizer. So please go through it and understand what's actually happening in here. It's explained in the write-up. So here we set our gradients to 0, get read from our data loader, and send our data, our input data to the device, and just call the forward method of our models with the right input to get the raw predictions and attention weights. And then we maybe create some mask to convert them to cast them to float 32. And then we use our mixed precision to back propagate the loss and do the optimizer step. Then we update our mix AMP, okay, for the mixed precision. And of course, we get our running loss, the perplexity, and also the running perplexity. We do our update in TQDM, and all the training process is as you've seen in the previous assignment. And for the validation, it's similar to the train, but I want to highlight here, because decoding takes quite some time. So on the entire validation data set, it might take even an hour to decode it. So we do our validation on just the first 5 batches. So that's why at the end, we divide our running distance by 5, just because of we're doing this over the first 5 batches. But after training your model, and we expect you to do the full validation, which now runs on the whole data. So once you run this part, please be patient because it might take some time. So we have the weights and bias setup, okay, and we recommend you using this to lock your ablations. So here you need to enter your login key, and this is also another way in which we are showing you how to name your runs on weights and biases so that your study group can use it. And since you're at the end of the semester, we are giving you all of these, the industry standard of doing this, so that once you leave from this course, you're able to use it. You're able to use it outside of CMU, and you're able to organize your runs better. So you have to enter your key and also create this project in your weights and bias account so that you can lock the runs under this project. Okay. And the next part now is our experiments. So we have a checkpoint directory where we're helping you to store your checkpoints, and we are saving the checkpoints after every epoch, as well as the best model loss, the best loss which you've gotten so far. So a lot of these are implemented for you, and if you want to resume logging, which is of course a hyperparameter, then you can load from those checkpoints and load your model state dictionary and your optimizer state dictionary and your epochs to resume training. Okay. So again, we providing you this so you understand the standard way of doing this since you're at the end of the semester. And we would also want you to understand how these are done in the industry. So it's also one of our learning objectives. So we start our login for the weights and bias. Okay, and once we call the forward method of the train, once we call the train model function, given our model, it returns the train loss, perplexity, and the attention weight. So we log the train loss and the perplexity on weights and biases, and we get our attention weight, which will depend on like the number of decoder layers which you have. So if you have a single decoder layer, you should return the attention weight for just that decoder layer. So this is for the cross attentions. Okay, so we are validating after every 2 epochs. So because the validation takes some time, so we don't want to do that after every epoch. So you can change this to maybe do it after every epoch or after 3 epochs. It depends on you. And after that, then we are able to save our model, and instead of plotting the weights, we are saving them so that you can always refer back to it. And now after the training is done, we actually want to call our validate on the full validation data set. So that will give you the actual validation distance. And similar to other assignments, you need to generate your predictions and submit them to Kaggle. So the next part that will complete like part 1 of the homework, which, as we said, it's using the CNN LSTM encoder and a transformer decoder. So Brett, this model will not be the best model, and can we perform better? Yes. So the CNN LSTM actually helps us to extract some representations from our MFCC, but they have no modules like positional encoding, which helps us to determine the position of each token, and it also doesn't have the attention mechanism, self-attention mechanism, which would help our models to know how the relationship between a token at a particular time sequence T, how it relates with a token at a different at another sequence. So for improved performance, it's recommended that we try to add this information to our encoded sequence, to our encoded embeddings. And the way we do this is by adding some encoder layers. So the CNN LSTM will help us as input embedding to our encoder layers, but now we would add the positional encoding to help determine the position, to help know the position of those embeddings, and also we'll add self-attention mechanisms for us to understand how each embedded token relates with the other tokens. So in order to do this, then now we'll have to create the encoder layer, which is similar to the decoder layer which you finished in part 1. So it's about you following this architecture. All the modules have been given to you, so it's for you to initialize them and call the forward method. And similar to the decoder, we also have now the encoder class, which combines the encoder layers, the positional embedding, and also the positional embeddings, and also the input embedding. So here we would see that our input embedding should be our LSTM, CNN LSTM network, which we created above. And after that, we have now a class to build a full transformer, which is an encoder with self-attention and a decoder with self-attention and cross-attention. So here we set up our full transformer, and we load the best model which we've had so far from the previous model. So here we call this full model, and the model here represents the part P1 model, because we will be needing the weights. And next thing we do is we want to copy the weight of the input embedding. Okay, sorry, this should be embedding, since we called it here as embedding. Okay, so we want to copy the weight of the embedding and get the encoder state dictionary. So if we remember our previous model, the whole CNN LSTM acted as the encoder, but here it's acting as just the embedding to our transformer encoder. So we will need to load that state dictionary and set it to our model. And next we are going to freeze the weight. So since we already trained it, we don't want it to change. We want to focus on training just the encoder, so that the encoder understands the range of values needed by the decoder. If not, then introducing the encoder will introduce a complete different representation which the decoder is not aware of, and it will result to poor performance. So we can think about what we are trying to do as some initialization strategy. But how do we initialize that? We do this initialization by freezing some parts of the model and forcing the updates on just some parts of the model. So we do the same for the decoder. We load the decoder state dictionary. The decoder hasn't changed from the previous part, and then we freeze the weight. And next we want to do is reset the optimizer and scheduler state, and we can do that by running the codes above where we were initializing them. And after that, we continue our experiment. So we create another directory which will store our full transformer checkpoint, and we perform again another experiment. However, what happens here is after 3 epochs, we want to break. Okay, so the reason we are breaking is because our objective is to train the whole model. It's not to train just the encoder, but we were using the weight freezing just so that the encoder understands the range of values which are required by the decoder. So after 3 epochs, which the encoder must have understood this range of values, we are breaking. And once we break, then we unfreeze now the whole network. So the embedding layer, which was frozen, we now set unfreeze it so that it can learn fully. And once this happens, then we are now able to re-execute this code and remove this break statement and let our model train. And we expect you to get improved performance than your part 1 submission. And this, after getting improved performance, then you should generate your submissions and submit to Kaggle. So improving your model, you should think about the input embedding. Can you have something better than this? So as we suggested, if you had a better performing encoder in your homework 3 P2, then you can also think about using that here. and you should think about the number of heads for the transformer modules. So we know the number of heads with multi-head attention helps the attention mechanisms to focus on different parts of the input sequence simultaneously. So you can think about that, and also think about the parameters which we described above. How can you improve them? So here we use a technique called incremental training. Okay, so can we use this technique to gradually add different parts into the transformer architecture or something like that? So you should experiment with that. And also, if you have a problem, please visit the office hours or post a question on Piazza. We'll be ready to help you understand and solve any issues which you would have. However, it's mandatory that you start early because there are a lot of moving parts, and you would definitely it's most likely that you'd face a lot of difficulties, but we're there to help you. And before asking before visiting the office hour for a question or asking a question on Piazza, please make sure at least you've read the write-up, understood it, and read the speech transformer paper, as well as the attention is all you need paper. And thank you for being part of the course right up to the end. We hope it's been quite a learning experience for you, and good luck. Thank you.